This is the second day of notes on section 4.3. And remember, in the first day of notes, we were discussing how when we have functions that when graphed, even something as simple as, say, f of x equals 2, and I go graph it, that the notation for finding the area under the curve, maybe from 1 to 5, can be denoted as the integral from 1 to 5 f of x dx. And as long as our function makes a geometric figure, we were able to use our geometry skills to figure out what the area under the curve was. We're going to continue with that today, and then eventually we're going to move away from the geometric part of it, because what if the function f maybe looks like that when we integrate or look for the area under the curve from A to B does not make a common geometric figure. Is it still possible to get its area, and how is that linked to our integration process? And that's one of the huge big things that calculus was able to conquer, and we're going to be doing that in section 4.4. But for today, we're just going to continue working with the geometric aspect of it. So all your areas will be basic rectangles, triangles, circles, semicircles, trapezoids, and all that good stuff. So this is the graph of f up here, and it's below the x-axis from -4 to 2. What that means is when I discuss the integral, which is what I like to call gives the signed area, because f of x is below the x-axis, that actually will be negative. Dx is our change along the x-axis, and as long as we're going that direction, dx will be positive. So really, when I'm asking you to do the integral from 0 to 2 of f of x dx, really what I'm asking you to find is the area under the curve from 0 to 2, which would give me this quarter of a circle. Because it is under the x-axis, we would call that, and although it's not really possible to have negative area, we can have a negative integral. So the integral gives us a signed area. And so this is going to be negative because it's below the x-axis. F of x, or the y values here, are negative. So I'm going to get negative the area of that quarter circle. So all I need to do is find 1/4 of the area of the circle. And the area of the circle is pi r squared, and my radius is 1, 2. So I'm really just going to be doing -1/4 of pi times 4, which gives me negative pi. And that's the integral, and it's the signed area under the curve. Notice that the whole circle, if I went all the way around, has an area that's equal to pi r squared, or 4 pi. So let's move along to the next one. So on the next one, I'm integrating from 2 to 6. Well, from 2 to 6 would be from here to here. And I am going forward, so my dx is positive. I'm above the x-axis, so my f of x is positive, which leads me to just finding the area of that triangle. And it's going to be positive because it's above the x-axis, and I'm moving to the right. So I just need to do 1/2 of its base times its height. And its base is 1, 2, 3, 4 long, and its height is up at 2. So I would do 1/4 of 4 times 2, or 1/4 of 8, which gives me an area of 4. So I'm going to go put a little 4 right in there so you can see that. I could even put a little negative pi in that one. This one's negative pi. Or I could say that whole semicircle is -2 pi. The next one is having me integrate from -4 to 2 f of x dx. And again, I am going to the right, so my dx is positive, but again, my f of x is falling below the x-axis, so I'm going to have a negative integral, or the area, signed area, will be negative. So really, I just need to find the area of that triangle, and again, it's 1/2 of its base times its height, and its base is 2, and its height is 1. Oh, that's a typo. That should be a -1 right there. So it's going to be -1/2 of 2 times 1, or equivalently a -1. So the area of this is -1. All right, so the next one is integrating from -4 all the way to 6. Well, because I have it laid out so nicely here, I know that this is -1. I know that each of these are negative pi, or the whole thing is -2 pi. Again, all of that is negative because it's under the x-axis. And then I have my triangle at the end, which has an area of 4. So I can just add those all up separately. I have the -1 with this first triangle. Then I have a -2 pi with that semicircle, and then +4. So when I'm all done, the total would be 3 minus 2 pi. It's balancing out to be negative because more of it is under the x-axis than above. On the next one, I'm basically doing the same thing as this one, but I am integrating the absolute value. That doesn't mean I go take the absolute value of this. That means that as I travel along, I take the absolute value of f of x. So really what that means graphically, I'm going to erase some of this stuff on here. Graphically, what that means is the absolute value will pop everything above the x-axis. So I'd have this, and then I'd have this, I'd hit up at 2, and then I'd have that. So when I'm integrating the absolute value, really what it does is it takes all those negative areas and pops them up. So this would now have an area of 1, this would have an area of 2 pi, and this has an area of 4. And so my absolute value of f of x dx would be 2 pi plus 5. The last one. I'm adding a constant on to f of x. Really what that does graphically is it moves the entire graph up 2. And let's see what effect that has on the area. We have a property that says that for addition you're allowed to split it up. So I'm going to do f of x dx, and then I'm going to do just 2. This one I already did right over here, and it was 3 minus 2 pi. Now, what do I do right? Oops, I forgot to put the 2 in here. What do I do for this one? How do I integrate 2 dx? Well, remember, this is the function now. The function is y equals 2. So if you want to put a visual on that, up at 2, you have a horizontal line. We're looking at the area under the curve from -4, right here, the lower limit of integration is what we call that, to +2. So really it's a rectangle that has a base length of 6, notice that's the distance between these two limits, and a height of 2. So it's a 6 by 2 rectangle. Actually, I'm sorry, that was supposed to be, I'm sorry, I have the wrong, that was supposed to go all the way out to 6. So let me fix this. I just had a typo, or a righto, I guess you'd call it. I'm going from -4 to 6. So let's go -4 to 6, and I'm integrating the function up at 2. So I end up with this 10 by 2 rectangle that gets tacked on, which tacks on 20. Now let's think about graphically kind of what's going on here. When you tack a constant on like this, you're moving the function up. When you move the function up, you basically add a rectangular region to the bottom of it. And that's kind of an important concept. So I'm going to go back up here, and let's pretend that I were to take this triangle right here, just from here to here, and bump it up 1. So now my triangle would go from here to here. Notice that in doing that, I've added this rectangular region that spans the limits. So on this one, it would go from 2 to 6, or 4 by 1. So really, it's going to add a 4 by 1 rectangle. And one more time with that, just so you can, suppose I had a fake function and I was going from -2 to 8 f of x plus 3 dx. What that plus 3 really does graphically is it moves the function up 3 along the limits from -2 to 8, which is a 10 gap. So what it's going to make when you do that is a 10 by 3 rectangle, or it's going to accumulate 30 more to the area of the function. Kind of cool. All right, so back to this one, it would be 23 minus 2 pi would be my area. So let's move along here. So the area under the curve we are noticing can be found by integrating with these limits of integration that are on some closed interval from a to b, and we've been calling our function generally f of x, but again, that's arbitrary. It could be called anything. We call this a definite integral. Definite integral, whereas when we were at the beginning of the chapter, we didn't have those limits, and we were doing an anti-differentiation process that would give us the antiderivative. Now, how are they linked? Well, first of all, I'm going to explain the difference. The definite integral has these limits of integration, and it indicates area under the curve, and it gives us a numerical answer, like this equals some number that represents the signed area under the curve. Whereas the indefinite integral does not have the limits, and that indicates to do a process. For example, when I did this in a previous section, we said, well, that's x cubed over 3 plus c. It gave me a whole family of functions whose derivative is this. It was a process called antidifferentiation. The definite integral is giving us an area under a curve or a number. Now, we're going to link the two, and we're going to link them really well, and it's so huge in calculus that it's actually called the fundamental theorem of calculus. We call it the FTC, the fundamental theorem of calculus, and it's in the top 10 math equations of all time. I'll have to look it up to see what number it is, but it made the top 10. It's a really big discovery. We can't work with it yet. I just want to tell you there's going to be a huge link pretty soon between our area under the curve with the definite integral and our anti-differentiation process with the indefinite integral. They are going to be married together in the next section. But until then, we're going to just kind of work with some properties and the geometry of it. So one of the properties when we have a definite integral that we can do is it's perfectly legal for us to change the limits of integration, but in doing so we're going backwards. So what happens is the dx, the change in the x, instead of going forward, you go back, becomes negative. So we have to put a negative in front of that. So anytime, for example, if you were integrating from -6 to 5 and you changed it to 5 to -6, that's legal as long as you throw a negative correction in front of the integral. When we integrate from a to a, like from 3 to 3 or 4 to 4, we'll always get 0. And really that's because we're not moving anywhere. There's nothing to find the area of. We have a constant multiple rule with integration that says your constants can come out front, just as they did with derivatives, just as they did with our indefinite integrals last week. We also have a property that says it's perfectly legal for you to split up a sum or a difference and work with them separately and add and subtract them. So it's legal to break that up. The next one says that to get from A to B, you can go from A to C as long as you then go from C to B. What that means graphically, let me just throw a fake function up here one more time, all my fake functions. If this is a blah, 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 f of x traveling like this, and I want to find the area under the curve, it's very obvious that if I went from A to C and then from C to B, the end result would be the area under the curve from A to B. And last but not least, it's also legal for you to change your variable of integration. I mean, I could call it f of k dk or f of q dq. It really doesn't matter. So there's no difference. So anyway, I put these all on here nice and laid out pretty, so in case you missed some of the explanation, you would have that. We're going to go figure out what this is, using the fact that they're going to give us a little help. And again, when we marry our two topics of definite and definite integration. With the fundamental theorem of calculus, I won't need any help. I'll be able to do this exactly and find the exact area under the curve without a calculator, without them giving me a few cheaters, and it's huge, and it's 4.4 is one of the biggest sections we'll cover all year. Anyway, what I'm going to do is use all the properties to break this definite integral up. I'm going to use the property that says addition and subtraction can be pulled apart, and I can view these as three separate functions of which I will then integrate separately. So I'm using the property that says go ahead and break up sums and differences. The next property I'm going to use is the one that said constants can come out front. And I'm going to go yank each one of these constants out front of the integral. The reason is because that's just giving me the x squared. So I want to get that negative out front. Same here. This is just giving me the definite integral for x dx. So I want to get that 4 out front. Same here, this is just giving me dx, so I want to get that 3 out front. Now replacing each of these with its integral value, in this case 26/3, plus 4 times, in this case 4, minus 3 times, in the last case 2, doing a little arithmetic, which would give me negative 26/3 plus 16 minus 6 is 10. 10 is 30/3. I get 4/3. Boom. Just a little numerical manipulation with that one. So this one's in your book. You're going to be doing a lot of the odds, so I nabbed a few evens out of here for us to look at. First of all, they're telling you some definite integrals, and you're going to use the properties to find other ones. So how do I get from 0 to 6? How about if I go from 0 to 3 and then from 3 to 6? And that's poor notation, but that's what I'm going to do, which would be 4 from 0 to 3, and from 3 to 6 is a negative 1, balancing out at positive 3. It's as easy as that. The point of this section is just to get you comfortable with the properties before we start to do some more important things. Well, what happened on this one? The limits were switched. Totally legal to do that, but they gave us from 3 to 6, so I do need to make sure I pull that negative out front. Whenever you change those limits, you need to take the opposite, so I'd have a negative 1 or equivalently 1. How about if I go from 3 to 3? Well, that's 0 because there's no dx in that case. It's basically graphically you're trying to integrate with no width. You have a graph that doesn't open, so there's no area. From 3 to 6 of negative 5, I'm just going to use my constant multiple rule and pull the negative 5 out front, and they handed me 3 to 6 as being negative 1. So it'd be negative 5 times a negative 1 yielding positive 5. And I'm not going to do all of these, but this is number 52 in your book, and it says to find the values of A and B to make this a true statement. If possible, you could use a graph if you needed to. Well, look what I've got going here. I'm hopping from negative 2 to 1 and then from 1 to 5. So really what I've done is traveled from negative 2 to 5. So A would be negative 2 and B would be 5. We're just skipping the middleman on that one. Instead of breaking it up, we're condensing it. It's kind of like instead of saying I'm going to go from Elk River to Rogers to Maple Grove, I'm just saying I'm going from Elk River to Maple Grove. Oh, we can skip that one. Let's go take a look at this one. I like it. This is saying find some limits so that the area under your curve will be negative, which seems counterintuitive because how can area be negative? But we call it the signed area. And so we're really looking at the graph of the sine function. And if you need unit circle to help you out, but you should have the sine wave memorized. Sine of 0 is 0. It's the y value right here. Sine of pi over 2 is 1, so at pi halves, I'm up at 1, which is the highest this can ever be. Sine of pi, I'm back to 0, and then sine at 3 pi over 2 is at negative 1, etc. And then when I get to 2 pi, I'm right back to 0. So my sine wave goes like this. And I'm supposed to put limits on my integral so that my area or my signed area is negative, which means I could use this piece. And I mean, there's a whole bunch of answers because this wave continues forever. I could use this piece as well. But I'm going to let a equal that limit of integration, which was from pi, and I'm going to let b equal 2 pi. And then I will be asking for this area, which because it's under the x-axis is negative or less than 0. Similarly, with the cosine wave, let's take a look at that. I want to have the area be 0. So really what that means graphically is I want to somehow balance out the amount above the x-axis and below the x-axis. Well, let's go graph that cosine wave. And again, if you need the unit circle to help you, you're certainly allowed to. Cosine of 0 is 1, so it starts up here at 1. Cosine of pi over 2 is 0, so it goes to 0 at pi over 2. Cosine of pi is negative 1, so it goes down to negative 1 at pi. Cosine, or the x value at 3 pi halves, is back to 0, so it's going like this. And then cosine at 2 pi, we are back to 1. And I did one full circle around the unit circle. Well, I need to have it balance out to be 0. So I either need to go forward some more to get another little piece here, or backwards some more, because I want to balance out my positive and negative area. So I'm just going to choose to go back here. So then if I travel from here to here, I've got this positive area, because it's above the x-axis, and from here to here, I have the same amount of negative area. So when I put them together, I'll get 0 as my total area. So my choice would be to have A go from negative pi over 2, start here, and then end right here at 3 pi over 2, because then I'll have this positive and negative area that are equivalent and cancel out to be 0. So the last one. This says, and this was multiple choice, this was in your book, number 60. You can see I'm picking some of the evens in here. 4.3 homework's really not due till Monday, but don't let it pile up on you too much. Feel free to start this at any time. Let's go take a look. I am approximating what from 0 to 9, 1 plus root x would be. Well, it's the area under the curve of 1 plus root x. Now, the square root of x does this. It's its parent function, but this is moved up 1. Or you could plot points too. You know, if you let x be 0, you'd have 1 plus root 0. If you let x be 1, you'd have 1 plus root 1. If you let x be 4, you'd have 1 plus root 4, or 3. And then let's go over here. If you let x be 9, you'd have 1 plus root 9, which is 4. So it would look like that. This notation means area under the curve. Well, you're out for sure. That's out because this is all above the x-axis, so there's no way its area is going to be negative. So I need to estimate the area of all of this stuff if I were to shade all that in. Well, just this part of it alone is a 9 by 1 rectangle. So just that green stuff at the bottom is 9, which means way too small, way too small. My only estimate that even kind of makes sense is 27. So that would be the best estimate for the definite integral. So the whole point of this, to kind of summarize it up, is we're working with definite integrals. Definite integrals have these limits. The notation indicates that when you have a definite integral, you're finding the area under the curve. And this had to be an estimate because I don't have a geometry formula for a shape that looks like this. So unless it's pure geometry, right now we're forced to estimate. But when it makes nice geometric figures like this, which was half a circle or half of pi r squared, and we got 2 pi and we realize it's under, so it's negative, then we can do it exactly. But our biggest dilemma is, all right, Now, how can I avoid estimating, still get an exact answer when my curve is all wackadoodle? Maybe it's that, and I want to find the area from here to here. How in the world do I do that without approximating? Because our Riemann sums, our LRAMs, RRAMs, and our trapezoids, those were estimates. And this geometry stuff is great. It is exact as long as it makes perfect geometric rectangles, triangles, and circles, oh my. But when we get all curvy wackadoodle and we don't make a geometric shape, is it still possible somehow to get the exact area under the curve? And you know, because I'm talking about it so much, that the answer is yes. And the process yields what we call the fundamental theorem of calculus, which is a huge discovery. It allows us to deal with curvature, and that's coming in section 4.4. But for now, we're working with nice geometric figures. Feel free to start on the assignment or continue to work on the assignment, and I am going to give you a little Schoology quiz on this, so make sure you digested the notes as well as just took them. Have a great one, guys.